This module is intended to introduce some tools of game theory that we'll use to describe how firms interact moving forward. So if you look forward either on the syllabus or Blackboard, whatever it may be, you'll see topics like entry and exit, pricing, mergers, those sorts of things. Almost all of these are topics where the firms are interdependent. Sometimes the firms are bidding against each other to acquire a new firm. They're competing in certain geographic markets. Their pricing differs depending on where they're at. All of these examples are situations in which a static model, where we simply graph out supply, demand, whatever it may be, and come up with price, may not be the most accurate measure of what's going on. Game theory allows us to more accurately measure and capture the true underlying strategy that is behind firm decision making. So in this video, the focus is on sort of what is game theory, two basic forms of games that we can get a lot of mileage out of. And then the next video, it'll be more applying them and making sure you're comfortable with solving different games so that when we get to different topics, we can take the game theory for granted and just simply look at how do firms behave in this given situation. Okay, so first I want to get some game attributes, some sort of terminology stuff out of the way before we get to two different games and how to solve them. The two game types we're going to focus on in this class are extensive form games, when the moves between players or competitors are sequential in nature. So one firm decides to enter a market, another firm responds by lowering their price, and then that first firm decides to leave the market after a while because they can't compete given that the other firm had lowered their price. Something like that, where the decisions are happening at different points in time. Normal or strategic form games are used when the moves are simultaneous or can be modeled as simultaneous. So two firms deciding maybe to advertise on the Super Bowl, something like that. Those are made at about the same time ahead of time. And so we can model those as a simultaneous move game. Other aspects of the game that we'll need to pay attention to are the players' interests, outcomes in conflict, or is there some common ground? So zero sum games are when if I gain, you have to lose, and if you gain, I have to lose. So we're in complete conflict. There's no mutual self interest, anything like that. Nuclear weapons, on the other hand, there's absolutely some common ground there, where not using them is beneficial for everyone involved. So, we'll use these games as need arises. Is the game played once or repeatedly with the same or changing opponents? Airlines are big users of game theory and pricing that stems from game theory, and we'll get to that later. But if a game is played once, we're going to tend to get one outcome. And it's going to tend to be the most probably aggressive outcome. We'll show that when we get there. But if the game is played repeatedly over and over and over again, which probably is pretty apt for describing firm behavior because they anticipate competing against one another many, many years going forward, we're going to get a very different outcome. Do the players have full equal information? If we have imperfect information, there's uncertainty, there's risk involved. If we have asymmetric information, one party might know more than others. So there's all kinds of these attributes that when we get to different games, we're going to have to try and figure out how to model these different things. Are the rules of game fixed? Can they be bent, changed? Is there first mover advantages? Can they reach agreements? Can they cooperate? Usually antitrust laws are sort of making that difficult, and we'll go through several different antitrust laws as they're applicable to the topic of the different modules, but in general, these are all issues. So, in terms of modeling the game, some terminology and assumptions. When we say strategies, We're talking about the complete set of choices available to each player. So it could be I can price high or low, or I can price at a different level, or I could advertise or not advertise. I could do all kinds of different things. Now, when the game is sequential, it becomes more difficult because my strategies are dependent on what's happened before me and what may happen after me. But it's still pretty straightforward to model and solve, and we'll talk about that moving forward. Payoffs, most often our payoffs are going to be profit, but they could be any number of different things. Oftentimes they're going to be expected profit because we're not going to know for certain. Let's say we're investing in research and development to develop a new product. We have an expectation of what the market will be and how in demand the product will be, but there's some risk and uncertainty built in. It could be just a set amount, and then how do we value that? So here I've got option A and option B. Do we value them the same, even though one's for certain and the other is an expectation? Depends on how we view risk. Finally, we assume rationality. We don't assume selfishness, and we don't assume that decision makers are perfect, but we do assume they're rational. They learn from mistakes, they learn from experience. They are maximizing things, but they're not maximizing necessarily at the expense of all else. So it doesn't assume selfishness, short term thinking. They can take into account any number of different things, and we can build that into the model. And then common knowledge, we assume that the players know they're competing against each other and they know what strategies are available to each other. There's some elements they may not know, but a lot they do know. Okay, so the most sort of stereotypical, the prototype game, if you will, for normal or strategic form where the actions are happening at the same time is called the prisoner's dilemma. So, according to the prisoner's dilemma, here's the situation, then we'll talk through modeling it and solving it. Two criminals are arrested. They're suspected of committing a series of robberies. When they're arrested, the police find drugs, illegal weapons. They find something on them that will allow them to put these two individuals into jail. However, they suspect these two individuals of more serious crimes, and they'd like to prove that they committed these more serious crimes. So, again, if you've ever seen any kind of Law and Order or TV or movie where it's arresting people and that sort of thing, they split them up in separate rooms and they offer them a deal that if you agree to testify against the other, we'll give you a plea arrangement, you'll go free, and the other will go to jail for a long time. If you both agree, if you both strike a plea deal, you'll go to jail for less time because you save us some taxpayer dollars in terms of running the trial. But if they both remain silent, the police can't prove the more serious crimes. So this is a game where the moves are made simultaneously. Because they're in separate rooms, they don't see what the other one's doing, so it's modeled simultaneously. Okay, when we do simultaneous move games, we model those in a game matrix. So the game matrix is just going to be a box, and the number of rows and columns in this box are going to be associated with the available strategies of each player. So in this case, the players have the choice of staying silent or confessing and testifying against the other player. So each player has two options. So we're going to divide this box into two columns and two rows. So up here, we're going to go, this is confess and testify. And this is going to be remain silent. And then over here, for the other player, this is going to be confess and testify. And this is going to be remain silent. And what we're going to put in these cells is the player's payoffs for being in that box. Okay, so if they both remain silent, so that's that lower right-hand box, the police can't prove the more serious crime. So they both go to jail for 1 year. So we're going to put 1, comma, 1. Now, I'm color coding this, but the usual convention is the left-hand number is associated with the row player and the right-hand number is associated with the column player. So I'm color coding them, but that's the rule I'm following. Left is row, right is column. Okay, the upper left, they both confess and testify, which means they're going to go to jail for less time. So let's make this an 8, comma, 8. So they both go to jail for 8 years. And then the two off-diagonal elements. One is confessing and testifying, so they're going to go free, and the other one is remaining silent. So the one that goes free is the one that confesses and testifies. So that means up here, this person's going to go 0 years in jail, and this person's going to go for 20. And then down here, this person's going to go for 20, and this person's going to go free. Okay, so this is our normal form representation. It's called a game matrix. The left-hand payoffs are going to be associated with the row player, the right hand with the column player. The next slide we'll talk about how to solve this. Okay, so how to solve this. The equilibrium to any normal form game is referred to as a Nash equilibrium. And basically, once we find Nash equilibrium, we've found an outcome where no player wants to change their strategy after the fact. So if you make a choice and then you learn what your opponent chose, if I ask you, do you want to go back and undo that? The answer, if it's a Nash equilibrium, is no, you don't. The way we find that, there's numerous ways. The easiest way, or at least the most straightforward way for our purposes, is best response analysis, where we look at what would a player want to do if their opponent made a certain choice. Okay, so for example, let's say that player 1 chooses confess and testify. Player 2 then has the option of they can confess and testify and go to jail for 8 years, or keep quiet and go to jail for 20 years. Assuming you don't like jail, you're going to optimally choose 8 years. So I underline that. You can star it, you can circle it, you can do any number of things. We then say, okay, what if player 1 instead chooses to keep quiet? If player 1 chooses to keep quiet, as player 2, my choice is confess and testify and go free, or keep quiet and go to jail for 1 year. And so my optimal there is going to be to go free. Now, we're not going to do it in this video, but you could think going forward, maybe if we're playing this game over and over and over, maybe 1 year in jail would be worth it to, get along well with my opponent. But for our purposes here, we'll deal with that when we need it. We're just looking at how would they respond. We then say, okay, if player 2 chooses confess and testify, player 1 can either go confess and testify and go to jail for 8 years, or keep quiet and go to jail for 20 years. So we're going to assume that they would prefer 8 years over 20 years. And if player 2 keeps quiet, then player 1 can either confess and testify and go free, or keep quiet and go to jail for 1 year. So they would confess and testify and go to jail, and go free. Our Nash equilibrium is anywhere that these best responses overlap. And you can have multiple of them. In this case, we have one, that upper left-hand box, where they both confess and testify and go to jail for 8 years. But any box where these overlap, where we have best responses overlapping, is going to be a Nash equilibrium. Now remember, Nash equilibrium after the fact, do you want to change? So if I'm player 1 and I confess and testify, and I find out that player 2 confessed and testified, do I want to change? Well, if I were to change as player 1, that would mean going from confess and testify to keeping quiet, which would mean my jail sentence goes from 8 years to 20 years. No, I really wouldn't want to do that. Okay, now extensive form, we model, it's called the game tree. We order the moves from the first move on. So let's take that same game and let's say that, let's say that player 1 gets to move first. And player 1 can either choose confess and testify, or remain silent. Player 2 then gets to move second. Okay, so this is sort of a little bit of an abstraction where we're saying that player 1 gets to first choose whether to take a deal or not, and then depending on what they do, player 2 gets to choose. So here's player 2, so call it P2, P2, and we're confess and testify, or silent, silent, confess and testify. And then down here at the end, what we're going to do is we're going to put the payoffs. So if they both confess and testify, they both go to jail for 8 years. Now, again, I'm color coding, but in general, the top number is the first player to move. The next branch over, so you can sort of see where it's getting game tree, so you can think of these as branches. Player 1 confesses and testifies. Player 2 stays silent, so player 1 goes free, and player 2 goes to jail for 20 years. When we move again over one more branch, player 1 is staying silent, player 2 is confessing and testifying, so player 1 is going for 20 years, player 2 is going free, and then the last outcome, they both remain silent, they both go to jail for 1 year. Okay, so again, this type of format for this particular problem is probably not all that accurate, but I wanted to give you a consistent story so you can see how you'd model those differently. Okay, so here's the exact same outcome, exact same payoffs, everything, but I've used a computer program to sort of model this. Instead of going from top to bottom, it's going from left to right, but either way works. Okay, so how do we solve this? We solve this through backward induction. And what backward induction says is when we have a game where the moves are sequential, we start at the last player to move, and we start, some people refer to it as trimming the branches. We start eliminating strategies that we know they won't choose. So for example, if we look at this spot right here, so that's where the blue player gets to move, and their choices, if they find themselves at this node, they're either going to get 8 or 20, so we can eliminate that as a strategy. They're not going to choose that. Okay, we then go down to this node here, which is also the blue player choosing, and if they find themselves at this node, they're either going to go free or go to jail for 1 year. They'd prefer to go to jail for 1 year, so we eliminate that branch. Backward induction then says once we've eliminated what the last player to move won't do, we move to the next player before them in terms of chronologically who moved before them. Okay, so we move out to here, and this player's now choosing between this 8 up here and this 20 down here, and so they're going to eliminate that strategy, and there's going to be our equilibrium to the game. Now, it does not have to be the same equilibrium as we get in normal form. In this game, it happens to be the same, but it doesn't have to be. And we'll run into games as we proceed where it isn't. But in this particular case, it is. But we use backward induction anytime we have an extensive form game where the moves are made sequentially, where we start at the end, we eliminate what they won't do, and then we sort of move ourselves backward chronologically, which is where we get the backward induction, eliminating strategies until we get down to one that survives.